In the next question we have solid mercuric oxide decomposes as per the equation HGO solid giving Hg gas plus half O2 gas if a total pressure of 141 mm was recorded at equilibrium at 653 Kelvin temperature. If the enthalpy change, once again here in this question, enthalpy change is involved, which is given as 142.7 kilojoules. Assuming partial pressure of oxygen in air is 160 mm, find the temperature at which this HGO solid dissociates freely in air. So what is given is the system HGO solid undergoing dissociation to give Hg gas is given in gaseous phase plus half O2 gas. This is the system and it's given temperature T1 as 653 Kelvin and enthalpy change delta H at the given temperature is 142.7 kilojoules. So 142.7 into 10 to the power of 3 joules per mole. And later it's given as partial pressure of oxygen in air is 160 mm and we are asked to find out the temperature T2 at which the solid mercuric oxide, if kept in open air, undergoes dissociation. And if we observe this given system at equilibrium, what we find is that every 1 mole of solid dissociates, we get 1 mole of this and half mole of oxygen, both are gases. In other words, the mercury vapor and oxygen are always liberated in the ratio of 1:2, 2:1. And it is mentioned that the total pressure P total recorded at equilibrium because of these two gases is 141 mm. In other words, mercury vapor corresponding to 2/3 of 141 mm, that is 141 by 760 atmospheres. And whereas this oxygen part corresponds to 1/3 parts of 141 by 760 mm, which will become partial pressures of these two gases. So let us find out what is the equilibrium constant Kp at 653 Kelvin temperature. Therefore, Kp1 in terms of partial pressures at temperature 653 Kelvin is given by the partial pressure of mercury vapor, which can be written as 2/3 into 141 by 760 into partial pressure of oxygen whole to the power of half from the system. And what is the partial pressure of oxygen? 1/3 into 141 by 760 atmospheres whole to the power of half. So this all comes out to be Kp1. And if we take this 141 by 760 as 0.186 atmospheres and work out, this Kp1 comes out to be 0.031. If you go for the unit, atmospheres whole to the power of 3/2. So that is Kp1 at the given temperature of 653 Kelvin. But it's given the partial pressure of oxygen in air is 160 mm. That is 160 by 760 atmospheres. When this is the partial pressure of oxygen in terms of atmospheres, the partial pressure of mercury vapor is supposed to be double because there will be always in the ratio of 2:1. So therefore 2 into 160 by 760 atmospheres. So the equilibrium constant as per this Kp2 will now become partial pressure of mercury vapor is 2 into 160 by 760 atmospheres and that of oxygen is 160 by 760 whole to the power of half from the given system. And when you simplify this, it comes out to be 0.1932 atmospheres. Now why this Kp1 and Kp2 are different? Because the temperature will be different now. So how are this Kp1, Kp2, T1 given and T2 are related? So how is that the equilibrium constant changes with the change in temperature is the basic point involved in the question. So we have an equation log of Kp2 by Kp1, equilibrium constant in terms of partial pressures at two different temperatures is given by delta H by 2.303 R molar gas constant into T2 minus T1 by T1 T2. So this is the relation which is to be used Now we know Kp2, we know Kp1, we know delta H, we know R, we know the T1. So what is left to be worked out? T2. So that T2, they are asked to find out where solid mercuric oxide dissociates freely in air. So therefore, substitute the values. Log of Kp2 by Kp1, that is log of 0.193 by 0.031 is equal to delta H 142.7 into 10 to the power of 3 joules by 2.303 R. R is 8.34 because we have to express in joules into T2 minus T1. T2 we need to find out. T1 is given as 653 by T2 into 653. Now we need to simplify this, which is tough. Then how to save the time without simplifying, can we work it out? So we need to check with the options given. The first option says 702 Kelvin, but the second is 653. First temperature is also 653, second temperature is also 653. And if we substitute that 653 in the place of T2, this becomes 0. So the whole value becomes 0. Log of so and so will not become 0. So therefore, B is definitely wrong. And it cannot be less than 653. In that case, this value, if it is less than 653, it comes out to be negative. Therefore, even C option is wrong. So the answer lies either in A or D. And 702, 1014. So D is double to this. So one of the values, say 702 Kelvin from A option. Let us substitute in this and verify whether you get this ratio or not. That is the better way of cross-checking the answer. So if we substitute 702 in that and cross-check, we get this ratio of log of 0.193 by log of 0.031 nearly comes out to be log of 6.23. In other words, if this right hand side by substituting 702 Kelvin in the place of T2 comes out to be 6.23, then we are right. So we need to check by putting T2 is equal to 702 Kelvin and cross check whether we get log of 6.23 or not. So that is the better way of simplifying and answering the question rather than going for each and every value. So the answer comes out to be 702 Kelvin rather than 1014 Kelvin. Hence the answer is A.